The next topic is a pretty big topic. It's related rates. So this is just talking about derivatives in context in a different way. So to start, we'll look at this question. The volume of a cylinder with radius of 5 inches is increasing at a rate of 36 pi inches cubed per minute. How fast is the height changing when h equals 10 inches? So to start, let's draw this out. Let's go to a whiteboard. We can clear this. So we had 5 inches, 36 pi, and h. So that's a bad cylinder. I'm gonna redraw one. It's a slightly better cylinder. So we know that the volume of the cylinder with a radius of 5, so R equals 5. I don't think you can see this right now. I'm just writing it down so we remember. R equals 5. Height equals 10. Ooh. Oh, and it's all back. Okay, let's try this again. We have a cylinder. The radius of 5, which is constant, 5. And the height is changing at a rate of 36 pi inches per second. So we're going to write this as the derivative of the height. So dh with respect to the time. So how fast is the height changing over time? And they said that that was 36 pi inches cubed per minute. So now we're asked to find how fast is the height changing when h equals 10. And we have to remember that this h right here is not constant. Not constant. And this is constant. Okay, so now we're looking for how fast is the height changing. Oh, wait, I'm sorry. Sorry, this is not the change in height. This is the change in volume. So this is like we're adding water to a cup that's cylindrical. So the water is going in at a constant rate, but the height we need to find the rate that changes. So we know that the area of a cylinder can be found, or the volume of a cylinder is found by V equals pi r squared, the area for a circle, and then times the height. So what we do here to find the rate of change of the height is we have to take the derivative of this, because whenever we're thinking of rates of change, we have to think of derivatives. So the derivative of the left. Now, V it's like our y. And when we take the derivative of something that's changing, we have to remember to use the chain rule. So the derivative of V, if we're taking, we have to take it with respect to time. So dv dt, it's about t, equals, and now if we use product rule, we have pi r squared. So we do lefty right. So pi r squared dh dt plus right d left. So h times the derivative of pi r squared, which is 2 pi r. And then this is the expression, oh, can't forget that when we're taking the derivative of something with a variable in it, we have to multiply by its derivative with respect to time. So 2 pi r dr dt. And now we plug in what we know and solve for our unknowns. So we know that dv dt, like up here, is 36 pi. So we'll have 36 pi equals, the radius is always 5. Oh, I think I messed something up. Sorry, we're gonna have to go back here. Okay, that would have given us 2 unknowns, so it's important to not make that mistake. We know that r is constant. So before we take any derivatives, r, we have to remember that r does not change in a cylinder. So we plug that in before we take a derivative. So we have v equals 5 squared, r is 5, and 5 squared is 25. So 25 pi h. Now we can take the derivative. So we have dv dt equals derivative of 25 pi h. We have to remember to use the chain rule. So 25 pi, h goes to 1, but we have to multiply by its derivative, dh dt. So notice that this derivative expression does not include h anywhere. It includes dh dt, but not h. So, and that's because if you think about it, when we're adding volume to this cylinder, its height is changing at a constant rate. It doesn't matter what point on the cylinder you are. The height here is going to be changing at the same rate as the height over here. It's not a cone, so, which we'll do later. A cone, the rate of change of the height would be different at different points because it gets narrower and wider as you change the height, but here it's not dependent on height. So now we can plug in our known variables. So we have no dv dt is 36 pi equals 25 pi times dh dt, which is what we're looking for. Now we isolate dh dt. So we have dh dt equals 36 pi over 25 pi. The pi's cancel out. So we get 36 over 25. Now let's see if that matches up with our answer choices. And sure enough, it does. Since we're adding water, the rate of change is positive. So we have 36 over 25, which was our answer. There we go. Okay, now this is a more difficult type of problem called a shadow problem. Just a little bit similar to a cone problem, but we'll do that in a second. So we're told a 6-foot-tall man walks towards a 30-foot-tall streetlight at a rate of 2 feet per second. What is the rate of change for the length of the man's shadow when he is 5 feet from the light? So first thing that we do is we draw this out. So we have streetlight, streetlight. It's not a light, but we'll pretend it is a light. And we have a man walking. Actually, that's probably a bad representation. And the light goes like this. which forms the right triangle. So actually, let's pretend this is the man's shadow. So as you get closer to the shadow, your shadow is going to get taller because you're going to be closer to the light and you'll be blocking more of the light. So if we pretend this, sorry, I'll have to redraw this. So this is our man, this is our shadow. Not the best representation, but we're looking for how fast his length changes. So we can split this triangle up into two pieces. These two are similar triangles, which if you remember from geometry, which I doubt you do, we're given that the height of the street pole is 30 inches, I believe. 30-foot tall street light, and the man is 6 feet tall. Make that look more like a 0. And we're looking for 6-foot tall man at a rate of 2 feet per second. And we're looking for it when he's 5 feet from the light. So let's call this distance x and this distance y. And these two are both changing with time. So we know that similar triangles, the ratio between the sides has to be the same if they're similar triangles. So 30 over 6, if we have that ratio, 30 over 6, that's a 30, not a 36, equals the ratio of this side on both of the triangles. So if we look the length of this whole side of the big triangle is x plus y, and then we're dividing it by the smaller triangle side, which is just y. And now if we clean this up by getting rid of the fractions, we multiply both sides by 6y. We have 30y equals 6x plus 6y. And then if you notice, we can take this 6y and bring it to the other side. And we have 24y equals 6x. So if we divide both sides by 24, we get y equals 1 over 4x. And this is going to be the same no matter where we are in the shadow problem. This ratio is always going to be the same because they're similar triangles. So now I believe we were given that the rate of change of the distance between the man and the pole, which is x, so dx dt equals 2 feet per second, I think it was. So he's walking this way. And now we can take the derivative of this part. So we have dy dx, dt equals 1 over 4 dx dt. Now, if we look at our given variables, we have dx dt equals 2. So we have dy dt equals 1 over 4 times 2. Or actually, it would be negative 2 because we're walking. No, it would just be 2. 2 times 1/4 is 1/2. So this is the rate of change of this width right here of the shadow. It's not a good drawing, but that's the width of the shadow, and we're looking for how fast it's changing. Now, if we go back to our problem, we'll see that 1/2 is on here twice. Looking if the length of the shadow is decreasing at a rate of 1/2 foot per second or increasing at that rate. So if he's getting closer to the shadow, to the street lamp, the shadow is going to be getting more narrow, because if when I did the problem, the rate of change of X was actually negative, because if we look back to the whiteboard, if we look, X is decreasing. So dx dt is really -2, not 2, because you're going to the left and this distance X is decreasing. So if X is decreasing, then we know that Y, because if we plug in -2 here instead of 2, then we get -1/2. And if a rate of change is negative, that means just something is decreasing at that rate. So now if we go back to this problem, we know that it's decreasing at 1/2 foot per second.